Okay, and our final talk for, I think, the conference is Noah Asano joining us to talk to us about our favorite topic, LLMs. And I believe they're online. We're just getting set up. Set. Okay, great. Thanks. Go ahead
All
and
right.
take it away.
Can you guys hear me all right?
Yes,
Okay.
great.
Uh, yeah, so you can just go through the slides as my talk progresses, but I'd like to thank everyone for having me here today. My name is Noah Asano. I'm a student at the University of Hawaii at Manoa, and this past summer I had the privilege of working on a really cool project with the Akamai Workforce Initiative at the Gemini Observatory. So yeah, let's talk about that. So at the Gemini Observatory, we manage our projects across many different platforms such as Confluence, Jira, Google Drive, Gmail, the Gemini Observatory logs, and other Gemini proprietary systems. And while all of these platforms offer unique benefits, having our information so spread out can make it more time consuming and difficult to find the information we need, stay updated, and coordinate effectively. Imagine this scenario. You're an engineer who just got to work in the morning, and before you can start working on vent gates or mirror covers, you have to go through all these different platforms and spend up to 20 minutes to get up to speed with what's going on. Now, this is very time consuming, and people don't have to just do this every morning. It has to be done throughout the day to stay up to date. So this all boils down to one question. How can we reduce the amount of time it takes to find information, stay up to date, and coordinate effectively when key information is spread across multiple platforms? We'll revisit that question in a second. Let's talk about large language models. So a large language model is a type of AI that understands and generates human language. If you've ever used ChatGPT, then that is an example of an application that it uses LLMs. And so you're at least a bit familiar with what they're capable of. These models can answer questions, summarize documents, or help draft emails. Standalone LLMs are smart, but they're kind of limited. They can only generate text. They don't have memory of conversations because they're stateless, and they can only answer based on their training data, and they can't interact with real world tools. So, to sum that up, uh, they are powerful but isolated. But recent advancements in AI have led to uh, the creation of LLM agents, systems built on large language models that expand their capabilities. It combines the language skills of an LLM with the ability to reason, take action, and remember context. LLM agents, or just agents for short, can understand and generate natural language just like an LLM. They can maintain memory across conversations. They can break down complex problems into steps. And this is a really important thing. They can use external tools like APIs and access data outside of their training and prompts. So agents don't just talk, they act. So now that we understand what LLM agents can do, let's look at how this applies to the Gemini Observatory. To recap, Gemini manages their projects across many different platforms, and with so much scattered information, it can take a while to find the right document, understand what's going on, and figure out what needs to be done next. So this summer, I worked on a full stack web application that uses an agent to aggregate project data from Google, Atlassian, and Gemini proprietary platforms. The agent that is accessible via the website was able to understand natural language questions, access and summarize information from project management platforms, and assist staff in completing basic tasks. So all in all, this agent reduces the time and effort it takes for staff to find information, stay up to date, and coordinate effectively. While I've mostly talked about the agent, since this is a full stack web application, there are a lot of pieces I had to create and architect in order to get this to work. A few things to mention are the OAuth 2.0 pipeline to get the user's Google and Atlassian credentials. Um, so about the stack, the application architecture and stack. I created a visual to help you understand the flow and connections in this application. That's on the next slide. And I'd like to focus on one part in this MCP down on the bottom. And what MCP stands for is Model Context Protocol. If you could go to the next slide, please. Well, MCP stands for Model Context Protocol, and it is a standardized way to expose your LLMs to external tools and resources. MCP allows us to define Python functions as tools and resources for our agent to use. Not just Python, but other languages too, like JavaScript. So it was originally developed by Anthropic to help language models safely and effectively interact with structured systems, APIs, and databases. MCP follows a client-server architecture. In this case, the agent is our client, and when it wants to use a tool, which is just a Python function, it sends a request to the MCP server using JSON format, and the server, not the agent, executes the tool, and then it sends only the response back to the agent. So I chose to use MCP for this application because of its modular design and safety. So MCP is modular and scalable. Because your tools are separated from your agent, things aren't tightly coupled, and it allows you to easily add and remove tools. If you want to add more tools to your agent, you can either code it yourself and add it to your custom MCP server, or you can check if there is already an existing MCP server for that and connect your client to that server. This makes it very easy to scale your agent. I'm sure there's a lot of concerns regarding the safety of giving a large language model access to our personal information. Uh, MCP is very safe by design because it creates an extra layer between the agent and the systems with your sensitive data, your Gmail databases or the Gemini proprietary systems. And you also don't have to worry about the agent executing arbitrary code because it's not actually executing the tool, it's calling the server to execute the tool, and the server only has access to the tools that you give it. So you don't have to worry about it doing anything like dropping a table from a database if you don't give it access to that tool. On top of that, if you remember, our server executes the tool and sends only the results to the agent. And since it only gets back the result of that tool call, you can control what data is exposed to the agent. You can scrub, filter, or redact anything you want before returning the data. And it also allows us to monitor interactions. I mean, since every tool call goes through MCP, you can log and monitor every single interaction between the LLM agent and the external systems. So in short, MCP helps agents stay flexible, safe, and scalable. So just to go through this part quickly, unfortunately, I was not able to have a live demonstration of the website, but I just want to go through like the flow of the application. So how does our agent actually use tools? Uh, so first, when we prompt the agent, it'll analyze our question and decide whether it can answer this with just its internal knowledge or if it needs to use external tools. If a tool is needed, the agent will send a request to the MCP server. The server will execute the tool. It'll return the results back to the agent. And the agent interprets the response and decides whether or not it needs to use another tool. So it works in like a loop. And then it'll execute that loop until no more tools are needed. And then it'll deliver the response back to the user in a natural, understandable way. So with this application, it was in the early stages, but I was able to test it with our platforms like Confluence and pull all the data from it and have it on a centralized dashboard. And I was also able to have it do things like run Elasticsearch queries on the Gemini Observatory logs and write and read emails from Gmail. So my project allows us to accomplish four main things. If you could go to the slide that says impact in future, please. Anyway, My project allows us to accomplish four main things. First, it reduces the time spent finding data. Instead of hunting through emails and all the other platforms, users can just ask a question in plain English and get the relevant information instantly. Second, it helps teams stay organized. By consolidating information from multiple tools into one central dashboard, the agent provides a clearer, more unified picture of project progress and priorities. Third, it lowers the barrier to interacting with complex systems. Users don't need to know how to run an Elasticsearch query. They can just ask naturally, and the agent will handle the rest. And fourth, this is the first agent of its kind, one that's specific to the Gemini Observatory. That what makes it different from existing agents like ChatGPT is the tools that I've given it, the custom tools that are meant to work specifically for the Gemini Observatory. I want to emphasize that this is pretty new, cutting edge stuff. This kind of application was not possible 2 to 3 years ago, but thanks to new technology, uh, we have the power to make agents that can satisfy our unique needs and make tedious stuff like project management a bit easier. So I'd like to thank the Solar System in Context for having me present virtually and accommodating me. I'd like to thank my mentors that helped me work on this project. I'd like to thank the Gemini Observatory for hosting me. And I'd like to thank the Akamai Workforce Initiative and its funders for supporting me and funding me for this project this summer. Thank you.
All right, great. Thanks very much. Um, let's see if we have any questions. I think I'm going to use my moderator privilege and ask one. So at Rubin, we've had talk about having an internal tool for documentation because some tools are a little complicated. Are the tools that you're talking about able to disentangle like public-facing stuff and internal-only LLM needs?
So for this project, everything that I did was internal. Um, yeah, like the Gemini proprietary systems that I was using, it was mainly tested with internal stuff, but I'm sure you could rework it to use public information.
Any other questions for speaker?
Again,
Hello. Uh,
oh, sorry.
oh, can you hear me?
Yes.
Okay. Um, so if you have a program that results in an error and you need to debug it, could you also use the AI to help debug the program?
Uh, yeah. So what you're describing sounds pretty similar to like IDEs that use AI currently, like Cursor, if you're familiar. And that's kind of what they do is they use a large language model agent, and the tools they give it are tools that allow it to edit your software. So remember I was talking about the tools make the agent. So if you wanted it to have the ability to edit software, you just give it that tool. My application specifically was didn't have that capability, but it is totally possible. Yeah. Thank you.
One time for one more quick question.
Yeah, I was wondering if you could share an example, a non-trivial example that was used with this tool.
Okay. So one thing that was really time consuming for the Gemini Observatory specifically is we have this database uh that keeps logs of like pretty much everything that the telescope does, and it uses Elasticsearch, and not everybody knows how to use Elasticsearch to run queries on that database. And I mean, it was really extensive. There was a lot of logs. And so I created one of the tools that I gave it basically taught the agent how to run Elasticsearch queries so that if you're the user, you can ask it, can you please find like error logs from this time to this time? And then it'll format the query for you and retrieve it from the Gemini Observatory logs.
Awesome. That's great. I know I hate looking through 20 years of logs. Great. Well, so with that, that's all the time we have. Let's thank our speakers once again.